Hi, this is Dave Johnson with another edition of Math Off Topics. Today I'm going to talk about related rates and give you an example of what I would consider to be a slightly trickier rates problem. In another video, I talked about my recipe for solving related rates problems, and I used a more straightforward example there. If you're having trouble with related rates, you might want to check out my other video. I will include a link to that video in the show notes below. So let's get to it. So let me read the problem to you. An inverted conical water tank with a height of 12 feet and a radius of 6 feet is drained through a hole at the vertex at the rate of 2 cubic feet per second. What is the rate of change of the water depth when the water depth is 3 feet? Okay, so I've gone ahead and drawn an inverted conical water tank and labeled the dimensions. So the radius is 6 feet, the height of the tank is 12 feet. And I'm showing the height of the water as y. So that's one of our dependent variables. Remember, the dependent variables should be identified first. And in this case, y is one of them. And then the other one is going to be the volume of the water in the tank. So, and then the independent variable, of course, is t. So now we're given that 2 cubic feet per second of water comes out. So we can draw that. And because it's decreasing the volume by that amount, I'm going to say negative 2 feet cubed per second. And that is our dV dt. So that's one of the pieces of information that we're given. The other question, the question in the problem is, what is the rate of change of the water depth or the height at 3 feet? So then our question becomes dy dt is equal to question mark when y is equal to 3. Okay. Now, we need to find a relationship between the dependent variables. So we know what the dependent variables are. They're the volume and the height or depth of the water. And what is the relationship between them? Well, we need to know the volume of the water in the tank. We don't need to know necessarily the volume of the tank. We need to know the volume of the water in the tank. So we still have a cone of water. Let me draw a vertical line here. It's going to help us to see that. Oops, let me do that again. And so I'm going to call this x, and that's going to be the distance from there to there, and that is the radius of the cone of the water. And it might help to maybe just kind of like draw a little cone here. And so x is the radius of the cone of water, y is the height of the cone of the water. Now, what is the volume of that cone? Now, this is one of the difficulties that some students have with related rate problems. It seems like you have to know all the formulas in the world, right? The volume of a sphere, the surface area of a sphere, the volume of a cone, and so on and so forth. That's sort of going to depend on your teacher, but usually your teacher gives you those formulas at some point, or at least tells you to know those formulas. So the volume of a right circular cone is 1/3 pi, and in this case, the radius is x squared and the height is y. So 1/3 pi x squared y is the volume of the cone of the water. Okay, so now it looks like we've got too many variables on the right side. We've got an x and we've got a y, but what is the relationship between the x and the y? Well, we can use similar triangles. Similar triangles often helps. That's not the only way to solve problems like this, and you may need other techniques, but what triangles am I talking about? Well, that triangle and this triangle. So those are similar triangles because they share the same angles. Um, and now, what is the fact that we use on similar triangles? Well, it's the ratio of corresponding sides are in proportion. So 12 over 6, so the height divided by the radius is equal to the height y divided by the radius x. And that's going to equal, so 12 over 6 is 2. Now, it's going to turn out that we really want to get rid of the x because we're looking for dy dt. So let's go ahead and solve this equation for x. So x is equal to y divided by 2. And now we can plug that in to our volume equation. And so we get v is equal to 1/3 times pi times x squared, but that's a y squared over 4, times the original y that we still have. And so I can rewrite that as pi over 12 times y cubed. Now we have our ratio or our relationship between our dependent variables. Okay, next step is to differentiate both sides with respect to t. So the derivative on the left is going to be dv dt, and the derivative on the right is going to be pi over 12 times 3y squared dy dt. Let's go ahead and simplify. So we get a 4 here that cancels with the 3. And let's go ahead and solve for dy dt. So dy dt is equal to, I need to remember to multiply both sides by the 4 and divide by pi and divide by the y squared. So 4 over pi y squared, and then times dv dt. And now we can plug in what we know. Remember, now we can plug in the y equals 3. So we get that dv dt is equal to 4 over pi times 3 squared. 3 squared is 9. Times, and then dv dt, we were given here -2. So -2. And if I simplify, we get -8 divided by 9 pi. And of course, that's going to be, now that wasn't supposed to be dv dt, that was supposed to be dy dt. And so that's feet per second. And so that's our final answer. And it's negative because obviously the height is decreasing when the volume is decreasing. So if you found this video to be helpful, please like and subscribe, and I will see you in the next video.